In 4.6, our objective is to use the trapezoidal rule to approximate area. Now, why, you might be asking, do we need to approximate area when we know how to do the definite integral, which finds the exact area? Well, remember that the definite integral requires, if we're going to do it the shortcut way, requires knowing how to do the antiderivative of this function. And then once we do the antiderivative, then it's easy, we just plug in the values, but we don't always have a function for which we know its antiderivative. We don't have a rule to take the antiderivative, so then we need to go back to where we started and say, well, let's estimate then that net area, because remember what that definite integral means, the net area between the function and the x-axis on a to b. So thinking back to when we started approximating area, we used rectangles, whether it was left endpoints, right endpoints, midpoints even was a pretty good balance between the left endpoints or the right endpoints, because instead of leaving out big chunks or including big chunks that weren't supposed to be included, it gave us a nice little balance. We also chose rectangles because it was the easiest area. We just said the length of the rectangle or the width of the rectangle times the height of the rectangle, and we did the length times the height, and that was it. That was an easy formula. However, even though it was an easy formula, it's not the best estimation technique. So what would be better than a rectangle? What would be better than just going up on the left side, or just going up on the right side, or just going up in the middle and then going straight across, straight across, straight across, and cutting out so much? Well, for a function that's slanted, how about going up on both sides? So here's our first subinterval. Instead of just going up on the left and then straight across, we go up on the left, we go up on the right, and then we connect it. Now, that's not a rectangle anymore. Now we have a trapezoid. Trapezoid is going to give us the best approximation, well, when we approximate, and we're splitting it up into a finite amount of subintervals, because we don't have to limit ourselves to just one side, but we can go up to the curve on both sides. So let's think about what a trapezoid is and what the area of it is. Why is this a trapezoid? Because a trapezoid has one pair of parallel sides. Those are the bases. So these are the parallel sides. So we'll call this base 1 and base 2, the lengths of the bases, and the height of the trapezoid is the measure perpendicular to each of the bases. So what makes this a trapezoid? It's a quadrilateral with exactly one pair of parallel sides. So think about a formula that you know pretty easily besides rectangle: triangles. We deal with triangles areas a lot. That area is 1/2 times base times height. So think about how the base of the triangle and how we can maybe turn this into a trapezoid. I like to describe it as a trapezoid is a triangle with its head cut off. So we cut off its head, and here's what we have. Now you cut off its head, make sure the way you cut it off is parallel to the base. So this creates a trapezoid. And we have a trapezoid where here are the two bases, the parallel sides. Call this base 1 and base 2. And the height is the measure perpendicular to each of the bases. So that's our height. So the formula is basically the formula for the area of the triangle, but instead of one base, we have two bases. So we're going to combine them by taking the sum of the two bases. So here's the formula for the area of our trapezoid: 1/2 base 1 plus base 2 times height. Very much like the area of a triangle, but it has two bases instead of one. So let's see how we can use this to find a better approximation. I'm going to draw two pictures and make sure that we've written down the area for our trapezoid. We'll draw this kind of like what it was on the other side. We've got two pair of parallel sides, those are the bases, and we're usually going to have the bottom of our trapezoid to measure the height, and usually the top is going to be slanty. So we'll call these our base 1 and base 2, the side being perpendicular to the bases right here. We'll call that the height. And then we'll remind ourselves of what the formula for the area of a trapezoid is: 1/2, and I'm going to write it like this, times the height times base 1 plus base 2. Now let's draw two versions of graphs here because we want to see what happens for different shapes of the graph. So I'm going to draw similar coordinate planes here for two different functions. And going back to this graph right here, notice that this trapezoidal approximation is all underestimating this curve, yet the curve is increasing and it's decreasing. But what it's doing the entire time that's not changing is this curve that you're looking at is entirely concave down. And this trapezoidal approximation is underestimating. So I'm going to show you two versions that will be the difference in them being one graph will be entirely concave down. We'll call this f of x. And then we'll draw one curve that's entirely concave up. We'll call this g of x. Other than that, I'm going to try to do the same subintervals so that you can see how it's different. So I'm going to start at 1, let's say mark off at 3, maybe then 7, and then 9. So I'll do that on the other side too. So I'm going to try to count off at 1. That'll be about 3. That'll be about 7. And that'll be about 9. So we're going to create an area here by going up to the function. And what we are going to show is an approximation of the area, the net area from 1 to 9 of f of x with respect to x. We're going to get an approximation for that. Squiggly equals for approximation. Over here, I'm going to show the approximation again from 1 to 9, but this function is g of x since I drew it with a completely different concavity. Oops, and I said 9 over there, but I just saw that I wrote 8, so let's fix that. Okay, so over here to the concave down function, we are, first I want to show the area of it. So it's this area that's bound between the function and the x-axis just from 1 to 9. So that area that's in there. Same idea over here. We are showing only the area from 1 to 9 between the function and the x-axis. So this region in there. Okay. Now we're going to split it up into the subintervals that are shown here. So we've got 1 and then go up 3 and then go up 7 and then go up 9. I like to show it as unequal subintervals just so you know that it can be equal, unequal, it's all the same in there. So here's our trapezoidal method. We go up on both sides because our area includes the measure of both of those base lengths. We connect from that end to that end. So our first trapezoid has an area that is the length of this base plus the length of this base is what we're adding up over here. Now each trapezoid has 1/2 in its area, so I can take 1/2 maybe factored out of all of them, 1/2 factored out everywhere. And the height in this case is the distance here that is the perpendicular to both of the bases. So the distance here is a length of 2. So 2 is the height times the length of the first base is whatever function value it takes me to get up that high. So plug in 1 to the function, so f of 1, plus plug in 3 to the function for this first base and get up to that curve, that's the function value at 3. So this is base 1 plus base 2. Add that to my second trapezoid. Well, this time the distance between 3 and 7, that's 4. And base 1 is plugging in 3, base 2 is plugging in 7. So plugging in 3 looks like this, f of 3. Plugging in 7 looks like this, f of 7. And then my last little interval is again 2 units apart. So let's see, where do we have some room? Plus the height times plugging in 7 to go up on the left, plugging in 9 to go up on the right, connecting them. So f of 7 plus f of 9. And that was my last trapezoid. I've got 1, 2, 3 trapezoids, 1, 2, 3 areas. Now we compute that and we get a value, but what I want you to see the most is when this function is concave down, when the function is concave down, what kind of estimate that we see. This is an underestimate because now we're going up on both sides of the curve and connecting it. So the straight line is going to be below how it's bending down. Over here, similar process, but notice how when I connect those, up on the right, up on the left, now it's overestimating. So think of when a function is concave up, like this function, that is an overestimation. Let's look at a couple of examples of how to use trapezoidal rule. When do we use it? Well, usually when we're told to use it. Such as this problem. The function f is continuous on 2 to 8, has values, now remember continuous, that's an important aspect of it because we got to be able to create area. Has values that are given in the table below using the subintervals 2 to 5, 5 to 7, and 7 to 8. What is the trapezoidal approximation of this definite integral? So it shows that we're starting at 2, ending at 8. So starting at 2, ending at 8, and we're using these subintervals. So we're saying from 2 to 5 is that first subinterval of a trapezoid. Now remember the formula for area of a trapezoid, 1/2 times height times base 1 plus base 2. That's the area of our trapezoid. So think of just finding each area. A half is in all of them. If we want to take out a half and use it individually, that's fine. How wide is it between 2 and 5? It's 3 units apart. So our first height is 3. We go up to the function value. This is our first base. We go up to the function value. That's our second base. So 10 plus 30. That's our first area. Our second area is the region from 5 to 7. That's 2 units apart. Base 1, base 2. So 2 units apart. Well, let's see. Did I factor out the 1/2? Let's see. Everything has the 1/2, so we'll factor it out. Base 1 plus base 2, 30 plus 40. Next and final subinterval from 7 to 8, 1 unit apart. 40 is one base length, 20 is the other base length. So plus 1, 40 plus 20. I've got my 1/2 factored out, so I don't have to worry about that. And there's my approximation. Now usually we want to evaluate it and make sure it's a number that makes sense. If we plug it in and solve it, we get 160. So our final answer is that we'd say the integral from 2 to 8 of f of x dx is approximately 160. Now, what kind of approximation is this? Without a graph, I don't really have a good answer. Let's go to a problem where we might have a good answer. The graph of a differentiable function f, differentiable we know implies continuous, on the closed interval -3. Now I said it implies continuous, but let's write that. That implies continuity. That's important to remember. On the closed interval from -3 to 15 is shown in the figure. The graph f has horizontal tangent line at x equals 6. That's important for another part of this question. Find a trapezoidal approximation of -3 to 15, the integral of f of t dt, using 6 subintervals of length delta t equals 3. So this is telling me that they all have the same height. The height of all of them is 3. So when I do the area this time, I don't just factor out the 1/2, I can also factor out the height of 3. So I have 1/2 times 3, and now I just have my base lengths. So 6 subintervals. So notice that -3 to 15 is already split up nicely into 1, 2, 3, 4, 5, 6 subintervals. So I'm going to do those function values. Go up on the left, it's -1. Go up on the right of this first subinterval, it's 0. So my first one is -1 plus 0. Plus the second subinterval is from this one to this one. So up on the left, it's 0. Up on the right, it's 1. So plus 0 plus 1. My next subinterval, go up on the left, it's 1. Go up on the right, it's 3. So 1 plus 3. My next subinterval, go up on the left, it's 3. Go up on the right, it's 1. 1 plus 3. Almost done. My next subinterval, go up on the left, it's 1, go up on the right, it's 0. And finally, last subinterval, up on the left, it's 0, up on the right, or down on the right, it's -1. And we can compute. Now, using a bit of symmetry here, we can do some work such as notice that these two, -1 plus 0, 0 plus 1, those are the same. Look at those net areas. That net area here, net it, put it together, negative and positive, those are gone. Here's another net area right here. Positive and negative, those are gone. So we add up what's remaining. This looks like 4 plus 4 is 8. Half of 8 is 4 times 3 is 12. So we get an approximation of our integral is 12. Now, decide where the approximation is an under or an overestimate of the actual definite integral. We just look at the concavity. So everywhere there's an underestimate is going to be because the function f of t is concave down. Concave down. We can see that it's going to be an underestimate because if I connect from end to end, that's beneath the curve. So that's underestimating when it's concave down. So where is the function concave down? -3 to 0, 3 to 9, and 12 to 15. Those are all the intervals where the function is concave down. Where is there an overestimate? Well, what are we looking for? It's going to be an overestimate because f of t, because our function that we're looking at in the graph is concave up. So where is that happening? 0 to 3 and 9 to 12. Concave up here, and then again concave up here. And that's it.